Okay, welcome everyone to this week's CDAC webinar. Today we're pleased that Dana Dlott from our sister campus of the U of I at Urbana-Champaign has agreed to give the talk. Like Yogesh Bora, who spoke last week, Dana was a charter member of CDAC when the center began in 2003 and remained a highly enthusiastic and very productive partner for many years. And for many years heading up the dynamic compression activities within our center. More broadly, Dana is widely recognized throughout chemistry, materials, and the shock compression community as a leader in fast spectroscopy of molecules and materials, for which he's won a number of awards, including the ACS Physical Chemistry Award in 2013 and a Lippincott Award from the Optical Society of America in 2015. Dana's bachelor's degree is from Columbia and PhD from Stanford, which he received in 1979. And that year he moved to UIUC as an assistant professor in chemistry, and through the years rose through the ranks, becoming a kind of institution at UIUC with appointments in the Materials Research Laboratory and as the Lichen Professor of Chemistry. And over the years, throughout this time, he's developed a lot of new spectroscopic and tabletop laser shock compression methods. Many of these are now in use in NSA labs, and he's also trained a large cohort of students who've gone on to the labs. And also, in the last few years, he's become incredibly productive, either in spite of or because he became emeritus professor in 2017, so he can answer that question for us. At any rate, we're pleased that he's agreed to give this talk, to give us some updates on his most recent work. Over to you.
Thank you very much, Russ, and thanks to everybody who's attending. I see a lot of old friends there. I did want to mention postdoctoral positions are available. So if anybody's interested, let me know. Okay, so I have a little outline. I'm going to talk about technique first. So I'll talk about the shock compression microscope. And then we'll talk about shock compression of things that don't blow up, like these metal organic frameworks and molecules in solution. And then I'll talk about the bombs. And we'll talk about temperature measurement and detonation and hotspots. Oh, let me give you the idea here. There's an inverted microscope, and you put your sample here, and here, maybe it's better to see here. We fire a conditioned laser pulse at a piece of aluminum foil, and we can accelerate it up to hypervelocity, and then we can shock whatever we're interested in, and then light comes out, and we measure that. Here I'm showing you a Doppler. I have a little thing that says Doppler velocimeter to measure velocities. I'll talk about that later. And we have an optical pyrometer to measure temperatures and a high-speed camera to get video. And we have actually all kinds of different lasers and flash lamps and stuff. Let's see, a couple things. One of the nice things about this technique, if you've been a laser spectroscopist, you always go, oh no, my laser's the wrong wavelength. But this is shooting bullets, and you can shoot a bullet at anything, I guarantee it. Even dark matter, I think. So it's got a lot of applicability. It is destructive testing though, one shot and kapow. So it's really useful to use single shot diagnostics and also to mass produce presumably identical samples. Sort of the secret sauce to making these little aluminum foil projectiles, which people call flyer plates, and they have the form of a disc, 0.5 millimeter in diameter and various thicknesses depending, is to have the right conditioned laser beam. So we have a powerful solid state laser, but it makes a terrible beam. And the way we correct this is we use this diffractive optic from this company, Cilios. And what it does is it's got a number of little diffractive elements, and each element has the property that when it's uniformly illuminated, it produces a uniform disk in the far field. So each of these small diffractive optic pixels is producing a disk. and then they all overlap. What's great about this is that when your laser alignment drifts, or even actually during the pulse, at the beginning of the pulse and the end of the pulse, the spatial profile is different. All that does is redistribute intensities over here, and it constantly maintains a very flat field so that you can launch a nice disk. Here's one of my labs. We're building, actually we're almost complete building a second one. This is the microscope, and people stand here, put their coffee there. And this is the big laser, and it goes through this pipe for safety, and it comes down here and launches the flyer plate. And then this is the Doppler velocimeter. There's some optics and electronics in here, and a fast oscilloscope and a readout. The optical pyrometer is fiber coupled, and most of it's down here on the ground, but all the fibers come up. There's a high-speed single frame camera and a high-speed multiple frame camera behind it. There's a femtosecond laser, and there's some nanosecond lasers back here. And there's a port in this thing so you can pipe whatever other laser you want to put in. So it's sort of like you stand at the deck of the Starship Enterprise, you put your sample under the microscope, you look at it, you focus it, you make it look the way you want, and you push a button and kapow, and then you sweep up whatever dust remains and put a new sample in. Because this is, I believe, largely a static high pressure community, I'm going to give the world's shortest shock tutorial. So here it is. This is some junk material, and it's at density rho naught. And here's a brick. And what I'm going to do is I'm going to generate a shock wave by dropping the brick onto the material. So when I do that, I launch a wave that goes through the material. And if the brick isn't moving very fast, it's basically an acoustic wave. So there's an acoustic wave front, but the density behind the front and in front of the front are unchanged. This is an acoustic pulse consisting of a lot of acoustic frequencies, and they have dispersion so that this wave front spreads out in time. So that's the acoustic case. Now, if I really send this brick going at high speed, I'll actually crush the material or compress the liquid I'm looking at. I'll still launch a wave, a front, and that's called the shock front. But what's different here is that the density behind the shock front is higher than the density ahead of the shock front. Because this is a fast adiabatic compression, you also get higher temperatures behind the shock front. Now, I want to tell you my favorite feature of shock waves, which is, I mentioned here that an acoustic pulse will disperse. Okay, but a shock front is a nonlinear excitation, and it steepens up. Here's one way of thinking about it, all right? This could represent, let's say, pressure or density versus position. And what I may have is okay, this is in front of the shock front, nothing's happening. And then here's the rise time of the shock front. And here I have a high pressure or high density. One way to think of this is you get higher pressures and higher densities with higher impact velocities. So what you have is up here where the pressure and density is high, it's actually moving faster than down here. And so it's going to want to steepen up. How steep is it? Well, in gases, it's a pretty solved problem. Okay, the steepness is how long it takes the gas to get up to this moving velocity, and it's a bunch of mean free paths. In solids, it's not a simple problem, and there's no simple solution to it. I will say that the fastest shock wave I've ever seen was in sapphire, which is very stiff, and it was 1 picosecond. So that's, the shock wave can be pretty fast, but you know, if you have an inhomogeneous material, we'll have some shock wave scattering, and it won't necessarily be so fast. All right, now, when shock research started, the primary tool was measuring velocities. And this can be done in a number of ways. I'll tell you the way we do in a moment. But what that historical work did is it established an equation of state called the Eugonio, which is a velocity equation of state. It's the velocity of the materials move, it's the shock velocity versus the velocity of the materials moving. And there's a bunch of, there's some short equations called the Rankine-Eugonio equations. And if you assume conservation of mass, you can measure the density from these velocities. And if you assume conservation of momentum, you can measure the pressure. So shockwave experiments are the primary pressure standard. So if you ever wondered, if you ever use, let's say, ruby chips in your diamond anvil, and you want to know how do they know how the ruby shifts with pressure, the answer is it's from shockwave measurements. Now, this classical model doesn't have temperature in it. So this Hugoniot is an incomplete equation of state. And one of the big things these days is to measure temperature and make more complete equations of state. Okay, now let's see. The speed of sound in air is 0.3 kilometers per second, or Mach 1. Obviously, it moves much faster in solids and liquids. And instead of being 0.3 kilometers per second, it's typically several kilometers per second. Now I want to do my favorite unit transformation, okay? A kilometer per second is equal to, now if you're doing a picosecond experiment, it's equal to a nanometer per picosecond. And today I'll only be talking about nanosecond experiments. These are experiments that use visible light, and the spatial resolution is typically, a couple microns. And so we'll be talking about microns and nanoseconds. And then let's see, Dave Moore, my friend at Los Alamos, always likes to say, a shock can pass over a molecule in less than a picosecond, and it can pass over a chemical bond in less than 30 femtoseconds. So it's possible to see some very, very fast effects. The problem is that to get really high time resolution with a shock wave, you need a thin sample. And the reason for this is that many of you are probably more familiar with using, short pulse lasers. Light travels at the speed of light. Shocks are about 10 to the 5th times faster. So the time it takes to excite your sample is the time it takes the shock wave to move from one side to the other. And so that limits your time resolution. And so one of the things we do is we try to arrange things where we have very thin samples. All right, now here's a calibration I like to do, shocks in water. These are the velocities that we typically achieve with our flyer plates, up to several kilometers per second. And before I walk you through this, I just want to say water, like it always is anomalous. Okay, so this isn't representative of too many materials. Water is low density because of the extended hydrogen bonded network. So when you shock water, it compresses a lot. And then when it compresses a lot, you get a lot of heat. So what you're going to see here is more compressible and higher temperature than you would if you were shocking, say, a plastic or a ceramic or a metal. Okay, so anyway, we can get pressures up to about 25 GPa. And I know we can go higher, but because I'm interested in chemistry and not metallurgy, that's not a range I'm real interested in. This is the temperature, around 2000 degrees. So that's pressure and temperature. And then I want to talk just the shortest bit about chemistry. So pure water has a chemistry that everybody knows. It can dissociate into protons and hydroxyl ions. I cannot say by how many orders of magnitude this is oversimplified, okay? But this is the concept that water, which is uncharged and hydrogen bonded, can dissociate into an ion pair. Now, the ion pair has a smaller volume than the hydrogen bonded water. And so the more you compress the water, the more the equilibrium is going to shift over to the ionic species. And in fact, up here, you're supposed to have a superionic liquid, which is it's all salts, it's all plus and minus, but it's hot enough to be a liquid. So that's really interesting because you can do ridiculous pH jumps, okay? You can start out here at pH 7, which means ambient 10 to the minus 7 molar proton, and you can get it up to 110 molar. So that really changes the water. So there's been a lot of work on water equations of state and water high temperature phases, but not much on the chemistry of these things. So that's something that we want to get into more. Velocity measurement's really important. We use this thing called the Photon Doppler velocimeter. And the way it works is you take a single mode laser, you split it into 2 pieces. One piece bounces off your flyer plate or your sample and gets returned, and it gets mixed with the reference over here somewhere. And out comes an interferogram. Every time this thing moves half a wavelength, you get a beat. By digitizing the signal and counting the beats or doing some other mathematical analysis, you can get a velocity history. And then, as I mentioned before, you can get pressure and density measurements this way. So using that Doppler velocimeter, here's some speeds of flyer plates. This is the range of the laser we're using now in terms of energy density. And the new system I'm building is 5 times as much energy, so that will be interesting. Our workhorse, and everything I'll talk about today, is 25 micron aluminum foil. And that's the thickness of the Reynolds wrap in your kitchen. But actually, for some reason, we pay 100 times as much for fancy aluminum foil. And you can see that with this aluminum foil, it's possible to get velocities up to about 4.5 kilometers per second. Now, the laser only has a certain amount of energy. If you use a very thin foil, you can make it go faster. If you use thicker foils or denser materials like copper, it'll go slower. So this is a little table of what you can achieve. And now I want to talk about what happens here. This is an experiment where this flyer plate is coming along at high speed, and it's going to hit a window, a cheap piece of glass I can afford to blow up constantly. And here's my Doppler velocimeter. And here's the output from one shot. Okay, so at first, this is 240 nanoseconds. Okay, at first, the laser fires at time 0, and this thing accelerates up. And at this time, it's traveling through a vacuum at a constant velocity of about 1.7 kilometers per second. And it's happy cruising along until it smacks into this window when it suddenly slows down. The speed of this drop depends on how flat and parallel this impact is. And we typically get less than 2 nanoseconds. And here I'm showing you the day we got half a nanosecond. So that's the time. Now you see the velocity doesn't stop, because when this hits the glass, it actually deforms the glass and causes it to flow. This is the period at which you have what people call steady shock drive. This is the flow being a steady velocity. And I can measure this velocity. It's 1.12 kilometers per second. And knowing the equation of state of glass, I can tell you it's 12 GPa. All right, so what you have here is you have a very sudden turn on. You have a period of constant shock, and then you have a period when the shock is declining. This is a reproducibility study. I'm just showing you a lot of shots. And here's what you want to see. There is about a 1% variation in velocity. To go 250 microns to hit the target, a 1% variation of velocity means the arrival time will vary by a couple of nanoseconds. So there's a couple of nanoseconds uncertainty as to when I'm going to hit the target. The very steep drop is constant. The flat part is constant. And the unloading is constant. The thing that varies the most is this 2 nanosecond variation in target impact. But it is really a very reproducible thing. And we've made it work very well and published a number of papers just on how it works and what kind of results we get. All right, so now let's talk about a project. I was contacted by a fellow at the Office of Naval Research saying that people want to be protected from shock waves. Let's say people are shooting guns or blowing up bombs. And they have, a number of ways of doing this, but he would like to try to investigate new methods for attenuating shock waves. And we came up with this idea, which actually I think came from Ken Susslick, my colleague, of using these things, metal organic frameworks, which are used these days for a million different applications. The metal organic framework here, this is a drawing, this is an inorganic chemist drawing of it. What you want to recognize is the big yellow ball really represents empty space. So what you have is you have a zinc atom and an organic molecule and another zinc atom forming kind of a cubic structure. So this is a nanoporous material, and it consists of these vertices and these intermediate organic molecules. And the stuff we're using has about 50% free volume. This is the, we wrote a paper which came out last December, where we reviewed this work on the accounts of chemical research. And my postdoc, Xuan Zhao, made a really nice drawing. These are little crystals of this material, which has the name ZIF8, which don't know what, zirconia, zinc, imidazole framework. number 8. And here it is getting squished, and of course nothing's happening. Here's my flyer plate. Okay, so the concept here, the new concept is to try and have a shock absorbing material that combines many different functionalities. So the first one is powder compaction. Okay, here is this ZIF-8 powder. And when you compress it, you compact the powder and that absorbs energy. And then inside each of these things are innumerable nanopores and they collapse. So I like to think of this as powder compaction. I like to think of as sand. If someone's shooting at you, hiding behind a sandbag is really good. Nanopore collapse, I like to think of as a sponge or foam or a mattress, okay? And then the third thing that's really never been done before is endothermic chemistry. Our concept was that when you smash this stuff, you can break a lot of chemical bonds. And that's the third mechanism for absorbing shockwave energy. Okay, now what I'm going to show you are shocks propagating through different thicknesses of this material. So this is a very thin 4-micron layer, so the shock isn't varied much. This is a shock lasting a few nanoseconds. And then as you increase the thickness, 20, 38, up to 110 microns, the transmitted shock gets smaller. Actually, 3 things happen. It develops the structure as a pedestal and a lump. The pedestal indicates powder compaction, and it also gets smaller. So what I wanted to do is I wanted to say, oh yeah, I can measure the absorption coefficient like I do in everything in the lab. But it's funny to do this because it's a shock wave. So we developed a method to do it that's described in that article. And what we did is we found what I want to call a mass-weighted absorption coefficient. So in other words, if you have this many kilograms of material, you'll get this attenuation. And the result we got was that this stuff is 7 times better than plexiglass. Okay, well, nobody is putting ZIF-8, in a product tomorrow, but it is a laboratory for investigating new ways of attenuating shock waves. Those of you who use diamond anvils are probably frequently recover your sample afterwards to see what it does. Often that's not hard to do in shock waves because the sample gets destroyed, but this one turned out to be pretty easy to recover. So let's look at it. This is the ZIF-8 before anything happens. There's the little shiny parts are where those little cubes happen to have mirrors pointing at you. This is how it looks in an electron micrograph. And this is after a 3/4 of a kilogram per second impact. Here's macroscopic what it looks like. If you look at here, it looks like this. And what's happened is the beautiful cubes have lost their structure, but you can still see individual cubes. When you hit it harder, it gets kind of mushy. And what you get are these flakes. So there's no more cubes, okay? You've totally destroyed the crystal structure. And when you blast it even harder, what happens is it gets sintered into a mass that I think I can best describe as carbon with zinc and nitrogen impurities in it. So here it is in more graphic form, okay? This is what the sample looked like before anything happened. It was a column 90 microns thick of this powder. And then the flyer plate's coming in up here, wham, and it's compressing. And we took it over to our MRL, and this is what it looked like. And I took off, there was a big piece of aluminum stuck on it, which I'm not showing. Okay, so the flyer plate hits here. So the shock is very big here, and as it moves through, it gets attenuated. So this one snapshot shows you material shock very hard, medium hard, very hard, medium hard, and not so hard. Then what we did is micro Raman spectroscopy. So we took Raman. Look, you can see it really falls into very nicely into 3 distinct zones. Okay, so the ambient Raman here before the shock is this. And I've identified some of the transitions, CH stretch, more CH bending, and so on. I think the one that's most interesting to me is this lowest frequency transition, which is the stretching transition of these 2 zinc atoms tethered together by this imidazole. And that's really low frequency, around 200 wave numbers. Okay, now if you look in this lightly damaged zone, the spectrum is just no different. There may be, I think I do see some very slight increases in the line width, but basically the unit cell and the molecular structure are unchanged, but the powder itself is crushed and compacted. So this is a zone of powder compaction. When I move into the next zone, and here's the Raman spectrum, again, the imidazole transitions don't look very different, but you notice this transition is gone. And that indicates that I broke the unit cell. Okay, breaking the unit cell means the nanopores collapse. So what I have here is powder compaction, nanopore collapse, and then up here I have this amorphous stuff, which doesn't really give any Raman spectrum at all. And that's what I wanted to describe as perhaps a carbon, zinc, and nitrogen composite. So I think the take-home message here is that there's a lot of room to look at shockwave chemistry, that this small sample tabletop technique makes it much easier to look at samples afterwards. And in addition, we can look at them in real time. All right, now I want to talk about something that's very new, time-resolved photo emission and absorption. It was being done by a Chinese visitor in my lab named Fabing Li. And what I want to tell you is that this is going to be a very general and powerful technique that's under development. So I'm not going to really be able to tell you a lot of science, but I'm going to show you the power of this technique. So the model system we used was this dye, rhodamine 6G and ethanol. It's got a really big, well-known spectrum. To study the photo emission, we turn on a 200 nanosecond green laser, and we look at the photo emission during the shock. To get the absorption in the visible, we have a little xenon flash lamp, and we detect it with a streak camera. That's for the absorption. And if it's an opaque sample that reflects, we can look at the reflection spectrum in the same way. So here's the result. This is the rhodamine 6G and ethanol, and this is a relatively low speed and a relatively low pressure. And this is the photo emission. So time zero, this is about 300 nanoseconds, and this is absorbed in the green. Okay, this is green, blue, red. And you see this nice, well-known rhodamine absorption peak. And then when the shock comes in around here, you get a peak shift to the red. The shock doesn't last very long, and so the peak shift goes away after that. But it's a convenient way of knowing when the shock is there. But there is an intensity loss. Photo emission is really easy to do. The problem is it just lets you see the parent molecule going away, losing intensity. The big new thing that we're doing now is we're doing optical absorption. So the nice thing about optical absorption is that if you shock the parent molecule and it turns into a new molecule, you may be able to see the new molecule. So this is the absorption spectrum here. Here's the absorption. It absorbs again in the green and also somewhat in the blue, but not in the red. And you can see here, you can see the red shift a little bit. And the absorption's around, and okay, so the result that I have here that I don't quite understand is that both the absorption and the emission got smaller, but didn't change in any substantial way. And I think the understanding of this is that this rhodamine reacted with the hot solvent and became something that doesn't absorb or emit anymore. Okay, now if you crank up the speed, all right, from 0.7 kilometers per second to 4 times that speed, then you get some big effects. Over here in the photo emission, you see this pretty good size redshift, and the photo emission just goes away. And then after about 50 nanoseconds, it comes back, but a lot of it's permanently lost. The absorption's doing some really neat stuff. There's a new transition here. And if you look down here at 300 nanoseconds, you've got this high structure here, all right? It looks like vibronic structure. We're still trying to figure out what this means, but my preliminary analysis is it's known that high pressure favors the formation of molecular triplet states rather than
deformation. We don't see anything.
There's somebody who needs to mute his microphone. Okay, so what I think is actually the vibronic structure in the triplet state. So really, these are the results we have. Well, let's see, there's one more result, which is we can take lots of data now. There's a lot of different speeds. And this is the emission intensity loss. At really high speed, it's really lost. At lower speeds, it's lost and come back. The absorption changes and so on. The message I want to send you here is that we can do this. And if you have materials that you think are interesting, because this absorption thing can be done in reflection. So I have a former postdoc who's looking at electronic materials, gallium arsenide and silicon, and metals and so on. Okay, we can do this. So I think that's the end of that section. And now I'm going to move into the energetic material section. So downloaded this from Wikipedia. Here's some gunpowder. This is a very early depiction of energetic materials. If you look really closely, this guy has a bomb and this guy has a gun, and this is from the 10th century AD. So they've been around for a long time. Gunpowder is what's called a low explosive. If I take this gunpowder and stick a match to it, it'll catch fire and fizzle around, but it won't blow up. If I confine it in a tube like a firecracker, it will blow up. I'm going to be talking about high explosives. High explosives use shock waves, and they'll blow up regardless of having any kind of containment. And it was Alfred Nobel who discovered this, I believe. He's the inventor of dynamite. And what dynamite does that gunpowder doesn't is it detonates. So here's a little depiction. Okay, so dynamite was kitty litter plus nitroglycerin. And here's a little exploding initiator, and it launches a shock wave. And the shock wave runs through here at supersonic velocity. The shock wave moves so fast that this stuff up here doesn't know it's coming and doesn't have time to get out of the way. So unlike the gunpowder that fizzles, you get an unconfined, very powerful, chemically sustained shock wave going through here. Detonation is a very special case. It's a chemically sustained shock wave where there's a balance between the shock energy and the chemical energy. So it maintains a constant shock profile indefinitely. Most explosives in current use are called plastic bonded explosives. And what they are is they're powders. So if you want to think a lot of explosives, you could think sugar as being a good surrogate, and glue. Okay, so if you imagine taking some sugar and a little glue, you have something the consistency of a plastic explosive. And one of the ones I'll talk about today is HMX, which is the most powerful one in wide use. And it has a detonation velocity of 9 kilometers per second, which is about Mach 33. And it produces a pressure of 40 GPa. Okay, so now I'm getting into the regime where I really care about temperatures. And so that's where we're doing optical pyrometry. So here's a drawing of our homemade optical pyrometer. So we have an explosion here and a microscope objective. And we have a little aperture here so you can select what part of the sample you're looking at. And then this is a prism spectrograph that has very high throughput but low resolution. And the red and green the red and blue wavelengths are imaged onto 32 fiber optics, which are imaged onto 32 photo tubes, which put their signal into 32 digitizers. The net result is that this thing measures what's called the spectral radiance. The spectral radiance is the spectrum, but the intensity is absolutely calibrated. And you absolutely calibrate it by putting a little 3000 degree calibrated source we have here. And it measures the spectral radiance every 0.8 nanoseconds forever. So when you get one shot here, you get spectral radiance from under a nanosecond out to, we usually stop around 10 microseconds because at that point, there's nothing much more than maybe a little smoke coming up. So the fundamentals of optical pyrometry are from the Planck black body distribution. So you all probably remember this from physics or chemistry. If you have a material at lower temperature, it emits red light. If you increase the temperature, the spectrum shifts to the blue and it gets more intense, which is happening here as well, okay? So what I'm showing you here is the spectrum of a black body. And we're in this spectral region here. And if you fit this spectrum, you can get the temperature. The other thing we fit is the height. Okay, now a black body, the height is characterized by a parameter called the emissivity, and it's maximum for a black body, or it's 1. So if I have a black body at 5,000 Kelvin, it'll look like this. If I have what people call a gray body, that is maybe the emissivity is a half, it'll have the same spectrum, but it'll be half the height. Okay, so what we do out is we take our spectra and we extract temperatures and emissivities. The purpose, so the temperature is the shape of the spectrum. The purpose of the emissivity is to learn how much of the material has reacted in a given time. So if you start out with transparent stuff, it has like minimal emissivity. But once it's burning and you're making free electrons and plasma, it has high emissivity. So with this measurement, you can get some kind of measure of the reaction progress through this intensity. And you can also get a measure of the temperature. Okay, well, we get 1 million of these. And instead of trying to plot them this way, we use this kind of plot here, which there are many names for. I learned this from Rich Yetter at Penn State. As you know, any funny function can be made into a straight line by messing with the axes. Okay, the specific axes you plot here are 1 over the wavelength and some complicated function that I'm not going to talk about right now. And so what this thing will do is, if it's a black body, it will give you a straight line. And it's important to know that, because what you're looking at isn't always a black body or its friend, the gray body. For instance, aluminum-based explosives always have lines where ALO is, or aluminum, and so on. So you want to be able to recognize the presence of non-thermal emission. That's why you want a straight line. The other thing I want to tell you is, in this plot, like, everything is backwards in the following sense. Normally I go blue over here, red over here, but since it's 1 over lambda, it's red over, or blue over here and red over there. And then normally I think, wow, you know, the more slopey this is, the hotter it is, but really it's the inverse. Okay, so what you want to remember, and I'll remind you, is that it's blue over here, red over here, and the big slope is hot, cold, and the small slope is hot. Okay, so here's a plastic bonded HMX explosive, 20% Silgard binder with a 4 km/s impact. And we're going to run from 1 nanosecond to 150 microseconds. And that's about, I forget, 50,000 spectral radiances. And then what we do is we do a log time averaging, so that each decade has about the same number of points. So bottom line is, we take the 10,000 or 100,000 points and we turn them into 70 points by averaging. All right, so what do we see here? Well, I see a very low slope straight line. It's always a straight line. Straight line, straight line, straight line. The slope is getting bigger, which means that it's cooling off. Okay, and so on. And I can make a little plot. So here it's getting around 6,500 degrees. And at the end, it's in the 3,000 degree range. And our interpretation of this from a lot of experiments is, at the very beginning, the shock hits this inhomogeneous material, and you get energy concentration at certain locations, and that produces a small quantity of very hot things, which are the so-called hot spots. One very prominent thing is if you have a hole or a void or a delamination or any place where you have basically nothing, you're going to get a lot of high energy right there and energy concentration. So the hot spots are very hot, and there aren't many of them, and they're small. And because they're small, they cool off pretty rapidly. Right around here, this stuff starts to explode. And when it explodes, the volume increases a lot and it cools down. So here it's cooling down. And now whatever's around is still burning at the nominal temperature around 3,000 degrees. Okay, now I want to tell you about TATB. TATB is a real good explosive for getting money to study. Because TATB is probably the hardest explosive to make go off. So it's the safest explosive. My friend Craig Tarver at Livermore says, if you have a block of TATB, if you shoot a 22 into it, it won't blow up. But if you shoot a 45 into it, it will. So this stuff is used in things you don't want to blow up accidentally, primarily the nation's nuclear bomb stockpile. The funny thing about TATB is it's yellow. And here's an absorption spectrum. TATB is the red here. So it absorbs down here, you know, in the green blue. And that means that when you're doing pyrometry, you're not going to get the expected signal in the green and blue. Just to show you here, this is an array of 200 little 1 millimeter diameter bombs made of TATB. That's the yellow stuff. This orange stuff is some Kapton tape we use. This is an X-ray CT scan of it. And TATB is miserable stuff, but you can see there are little holes in here, little voids, there, and there. And there's lots of big crystals and stuff. It's not real good. We can get much better results with HMX, where if you look here, it's really uniform. I think what you'll see is really tiny voids. There, maybe you can't see it, one there, and there's also a big crystal right here. Okay, but anyway, so that's the quality. So we can really mass fabricate arrays of hundreds of tiny explosives to study on a tabletop. And the mass of these explosives is anywhere from 50 to 250 micrograms. And so this is an inherently safe experiment because the quantity is so small. All right, now here's the same thing for TATB. And okay, what do you want to see? Well, right now it looks really hot, not so hot. It's kind of cold. Well, I'm sorry, it's pretty flat, so it's reasonably hot. Here's what you want to look at. It's not a straight line in a lot of places. Okay, and where's the deviation? Well, the way I think about it is it looks straight here, but then it deviates here. And this is the sign of the yellow material absorbing blue light. The absorption makes the signal weaker, and in this backwards plot, that makes this go up higher. And it's over here, which in the backwards plot is the blue. So this is the signal of blue absorption. And you can do two things. You can either fit the temperature to this part where the absorption isn't there, or you can measure the absorption and make a model for it. Anyhow, what happens is the TATB starts yellow, but as it decomposes, it loses color. And so you can see that at long time, see it's now a straight line, it's now a single temperature. Okay, so that's pyrometry in a nutshell. And now I want to talk about detonation. So what I'm going to talk to you about is nitromethane. Nitromethane has several advantages. For one, it's one of the few detonating high explosives that you can get in a bottle from the Aldrich Chemical Company. Number two is it's a liquid, and so you don't have to worry about all the fancy solid state stuff. And number three, it's transparency. You see right in there and see what's happening, unlike the plastic explosives, which are like looking at toothpaste. Now, nitromethane is a model system that people have studied for, gee whiz, a long time. There's a story here. I think nobody thought much about nitromethane. They used it to remove paint. But there was a railroad tank car full of it that derailed and fell over and it detonated and caused immense damage. And then people began to recognize that this stuff really was a high explosive and a nice model system. In the national labs, they do lots of experiments on this. They'll take a kilogram of nitromethane and they'll shoot a big flyer plate at it. And it'll take maybe 500 nanoseconds or a microsecond for the detonation to form. And so you need a really big sample to do this. We're trying to do it in a really tiny sample, okay? And so the way we do that is we use a technique called short duration overdriven subcritical shocks. Okay, short duration means this shock is going to last 4 nanoseconds, and it's faster than a lot of the chemical kinetics. So we get to time resolve some of the kinetics. Overdriven means that we make the pressure of the shock wave we're putting in a little bit bigger than a detonation. So it doesn't have to run up and grow and stuff. It just has to decrease a little bit. So we get the shock in the shortest possible time. And then subcritical means that we made the sample small enough that this detonation will go out quickly and not kill my students. So now I just want to tell you a really interesting feature of the nitromethane. So this tube here is supposed to represent nitromethane, and here's my flyer plate. And the flyer plate launches a shock, and this is the shock front here. And the nitromethane's reacting, and we see light from the shock front, so we call it the luminous shock front. But the nitromethane kinetics are such that it doesn't really start to explode for 2 or 3 nanoseconds after the shock goes in. In other words, there's a bunch of dark reactions that happen before the heat is released. So what you get is you get a luminous shock front, and then a few nanoseconds behind it, you get a delayed explosion. The delayed explosion launches another shock. This second shock is going through pre-compressed nitromethane, where it's really dense. So it's going really fast. And what it's going to do is it's going to catch up to this shock front, collide with it, and speed it up enough to turn it into a detonation. And there's this word that everybody loves. This is called the super detonation, because it's a detonation in a material that's already been compressed to higher density. But this is what you want to remember, okay? That there's a shock front with an explosion a little time behind it. And here's the temperature measurement. It very quickly, after a few nanoseconds, goes up to 3,200 degrees. So here's what the detonation looks like. What am I showing you? I'm showing you a velocity profile of the nitromethane shock as it comes out of the nitromethane. Okay. So this dotted line here is the shock we're putting in. It's 4 nanoseconds long, and there's this weak tail that's really too weak to do anything to nitromethane. This brown trace is what the shock looks like after it's gone through 30 microns of nitromethane. And the pressure has dropped tremendously. Okay, that's because the nitromethane is pretty soft and compressible. And so when the shock hits, it's like hitting a pillow, okay? You get low pressure and a lot of compression, but eventually you reach a place where it doesn't want to compress anymore, right? So that's why the pressure drops. Then what happens is you get this explosion. And this explosion produces a big explosion here, which is the super, and this explosion here is where the super detonation occurs. It's where these two guys merge. And then what it does is it decays. And in this region here, particularly these three here, magenta, orange, and I don't know what that is, green, olive green, the waveform's the same, and that's the detonation. And then it goes away because the sample's so small. Now you can photograph the nitromethane. So the way this was done is we just made nitromethane samples that were 25 microns thick, 40 microns thick, 90 microns, 110, out to 500 microns, and did the experiment and pieced this together. These are the photos. Now, what's happening here is you're the camera and the shock wave is coming to your face. Okay, so it's coming out of the screen. At very short time, we see isolated little explosions. You know, these are the hot spots. I don't know why they're there. People go, isn't there dust in your stuff? We filtered it. Are there bubbles? No, it's in a microscope. I can see bubbles. So this is some feature of turbulence, shock turbulence in a reactive medium. Once these guys start to blow up, they coalesce into this relatively uniform thing. And then this is taken at the instant, actually it's 5 nanosecond gate width. This is taken at the instant when the two shock waves collide. And then this is when you get the detonation. It forms this really beautiful thing called a cellular structure. And here it's dying away. The nice thing about the cellular structure is that we were able to use geometry to figure out where the explosion that caused the detonation happened. So we were able to map out a really nice time and space history about where the various explosions happened and when they happened. All right, so I'm going to close. Yep. I'm going to close by talking about another model system, which is a single crystal of an explosive that's encased in a polymer binder, because all the useful explosives have polymer. Also, what this does is it keeps this thing from flying away. And we're going to shoot a flyer plate at it. And the material is, this is HMX, the explosive. And this is polyurethane, which is a binder I'm using because the people who give me money like it. And here's what happens. Kapow, it blows up and we look at it. Okay, well, here's how it looked before we did anything. Here's this big sea of polymer with a little HMX crystal, and here's a blow up. This is an array of 90 of those, and they're not identical. Everyone's different, and we embrace the differences. This is how it looks afterwards. These cracks are caused, this is the size of the flyer plate. These cracks are caused by the flyer plate. That little hole there is when this stuff blew up. It blew up, it turned into gas, it vanished, and it looks like some of it squirted through this little channel here. Okay, but it definitely blew up. Finally, we take a limited number of these over to our X-ray analytical facility, and we do an X-ray image of it. And here is a roughly 1 micron resolution X-ray image of a really funny looking HMX crystal that we have been using. And here's the top of the polymer. Here's where the flyer plate comes in and so on. Okay. Oh yeah, that's a little delamination. That's a little internal void. These are little pointy things. You know, there's a lot of funny structures here. Okay, so what we do is we take this image and we send it to our collaborator, Uday at the University of Iowa, and they simulate it. So what they did here is they took one of our crystals and they simulated it without any holes in it, and then they simulated it. This one's got a channel, a void, like an elliptical, I don't know, a long canyon. That's a little canyon. And there's a little hole. And here comes the shock wave. And you can see a hot spot forming there. And actually, you can see hot spots forming in the voids. You can also see hot spots forming at the interface between the crystal and the polymer. So we get surface hot spots and bulk hot spots. And so the idea is obviously we do the experiment, he does the simulation, we refine his model and declare victory. Now I want to show you what I think is a really remarkable outcome of this. So here's an HMX crystal, and you can see a little hotspot forms, and then it grows some more, and then it kind of dies. And and this is the pyrometry. Okay, here's the temperature, and here's the emission intensity, or so-called radiance. You can make profiles of this thing. Okay, here's how it looks at this time. Here's how it looks later. Here's how it looks later. And you can see that it's growing anisotropically. Okay, it's growing in one direction. And the reason I think it's growing in one direction is, see, there's another hotspot there. This other hotspot heats up the intervening material, and so it makes it it's easier to make it react in that direction. Okay, but what's remarkable about this is that this is a method that allows you to take a reactive material and create a reaction that's localized in time and space. If it's initially localized in time and space, that makes it much easier to study how it evolves in time. And of course, what we're interested in is we want to build a kinetic model for the rate at which this material reacts at a given temperature. And so we can do that. We know the temperature, and here you can see how it's reacting. So this is very important because all the kinetic models people have ever made are for large things where it's inhomogeneous and the reaction occurs at many places in time. Finally, I want to show you spatially, so this is just spatially resolved intensity. Now I want to show you spatially resolved temperatures and emissivities. Here's an HMX crystal in a polymer, of course. And then when you shock it, what we've done is it's called either thermography or hyperspectral imaging. We took the spectrum in two colors, red and blue. Because I have two colors, I can get two parameters. The two parameters are temperature and emissivity. So here are, at 80 nanoseconds, you get hot spots in the red, and you get a different intensity in the blue. And at a later time, you get the red and the blue. By the way, just to see what's happening, what we did is we false colored the intensity and we superimposed the crystal on it. So before anything happens, you can see the hot spots are forming here, here, and here. There's no crystal here, all right? It's just, hot expanding fluid, but it just helps you see what's going on. So from the red and blue images, then you can do the following, okay? This is the temperature profile in space. Here are those three hot spots I mentioned. And as time goes by, they're cooling off. And you can see that in the pyrometry. Okay, they're cooling down. Here's the emissivity measurement. And as time goes by, the emissivity is going up. That means you're getting more reaction. And you can see it here. You can see that here's the initial reaction. You can see it spreading again in this direction. And this one is also spreading in a different direction. Okay, so by using the emissivity as a probe, we can measure the rate at which the reaction is going at a known temperature. When the temperature is constant, which it was, oh, don't have that. In this experiment, the temperature was pretty constant. Oh, was that here? Oh, here it is. Here, the temperature is pretty constant, okay? So then you can just look at the intensity. But when the temperature is changing, you have to look at the emissivity tells you the extent of reaction. So with that, I'm going to quit, hopefully in time. I want to give props to the people who did this work and also the people who funded it. And thank you all for your attention. And I would mention postdoctoral openings here.
Thanks,
So
Dave.
with that, I'll take questions.
Very good. Excellent talk. Beautiful work. I'm impressed by the number of applications you've been able to.
Oh, gee, I could have put in more, but I didn't. Let's see, what did my former department head always used to say? You don't want to overwhelm people, you want to just whelm them.
Okay. So we have time for some questions. There's already one in the chat from Philippe. Do you want to mute and ask it?
Yeah, how do I get to the chat room from here?
He's asking about the current limitations of temperature measurements sort of in general in shock compression.
Well, you know, you can put thermocouples into the material. They're slow and they perturb. Well, it depends. If your whole career depends on putting thermocouples in there, you're guaranteed to advocate they don't perturb anything, but obviously they do. So I really think optical measurements are the way to go. And the problem here is that when you look in the visible, the stuff has to be pretty hot. And our temperature floor is about 1800 Kelvin if we want to measure the temperature in 1 nanosecond. If I want to measure the temperature in a microsecond, let's say, I'm sure I can go to much lower temperature. If I want to go to even lower temperature, I can switch to infrared, and that's really a can of worms. It's not so fast and not so sensitive, but it can be done. The other frontier in temperature measurement, I think, is being sure that the light coming out of your stuff is really representing a temperature. And that's where our 32-channel pyrometer really stands out. People use single channel, double channel, 4-channel pyrometry, but I think they're often fooled by the non-thermal nature of the emission when it happens.
That's right. And in contrast to what's done in most static experiments, you're measuring absolute radiance, spectral radiance. And
yeah, of course, you can do that too. You just go by a calibration standard.
Yes, but most people aren't doing that in the.
Yeah, no, most people aren't doing that. No, that's why we're getting the emissivity, which, you know what, yeah, I'm starting to really love the emissivity. And the thing you want to remember is that the amount of reaction is linearly proportional to the emissivity, which is not, sort of, which is nice. But the emissivity is a high power exponential in the temperature. So it means that errors you make in the temperature measurement become magnified greatly in the emissivity. And so by having this thing with all these channels and you know, really high resolution, we're able to get good emissivity measurements in a short time.
More questions?
I have few small questions.
Go ahead.
Like, how do we decide, like, is there a way to find like where the hotspot is gonna be made before doing the experiment? Like,
yeah, no, I hear you. Right now, I think we're using random hotspots. And if they don't appear where we want them to, we just keep doing it until they do. So far, what we see is that the hotspots like to form, the surface hotspots like to form at the interface between the explosive and the polymer. And wherever you have those voids or cracks or stuff, the hotspots form. It would be really, really nice if you could make the hotspots appear on command. And hopefully in the next week or two, we're going to do that. I Googled what's the smallest drill bit I can buy. and I found 50 microns, okay? And so I think what we're going to do is we're just going to make a little 50 micron dimple in the crystal and see if we can't force the hotspot to occur there.
Okay. So
Okay, so interfaces, voids, and perhaps where we force it to have both those things.
so we can use something like STM tip to make a particular spot at a point, like crack the crystal at that particular position, and we can think that, okay, that's where the hotspot is gonna be there for sure.
Yeah, I'm worried the STM tip is too small.
Oh, okay.
So the deal with a hotspot is that they're fleeting, they don't last forever. And if they're very, and they die out because if they lose heat faster than they propagate, they'll die. When you've got such a tiny one, you've got a really high surface to volume ratio.
Mm-hmm.
And there's a guy, my friend Craig Tarver at Livermore, did a bunch of calculations. Basically, if it's a real teeny hotspot, it has to be really hot if it's going to live. And if it's a larger one, it can be cooler. But I think the ones you're talking about are so small that I don't know. I don't know that we can see them, and I don't know that they'll last long enough to see.
Okay.
The 50 mic, yeah, and on the other end of that, you've got the 50 micron drill, which is already getting big. But if you remember the way the drill works, it's a 50 micron cylinder, but it does come to a tip. So I think we can, I think we can put some really small things in there. You can also, focus a laser on it and ablate a little bit of it. So you can write your name in it and stuff and hope that the hotspot will go at the H of Hemley and not the R of Russ. So these things are all, we're thinking about, I think.
Great. More questions?
I had just one more small question.
Yeah.
You said for the direction where the hotspot is gonna move, it was kind of a particular direction where the hotspot was kind of increasing. So does it has to do anything with the crystal structure?
I believe so. So I showed a case where there were two hotspots.
Mm-hmm.
They kind of attracted each other because they heated up the material in between. The reaction was trying to go everywhere, and it just was much faster in that direction.
Mm-hmm.
Many combustion processes, the rate is limited by thermal conduction. Okay, I have a hotspot, and the rate is limited by the time it takes the heat to go into the unreacted material. These crystals do have anisotropic thermal conduction. And I saw Tommy here. I don't know if he's still here, but Tommy Sewell just published a paper on the anisotropic thermal conductivity of HMX. And so we're hoping that what we'll see is a hotspot going preferentially along the directions of high thermal conductivity.
Okay.
TATB has a structure like graphite.
Mm-hmm.
Planes with, weakly coupled to adjacent planes. And so I would predict that the hotspots would go in the plane and much slower out of the plane. Yeah. So yeah, that's a really interesting thing. We've definitely seen anisotropic reaction. Yeah. And so I know it's there, but what the mechanism is, we don't know yet.
Okay. Thank you. Thank you. It was a nice talk.
Yes, where are you from? Your name is?
Nikita, and I'm from UIC.
Oh, good.
And I'm with Professor Gluzak.
Fantastic. Well, I was supposed to give a talk at UIC and then the pandemic hit, but hopefully in the fall, next fall, I'll come up, and if you're still haven't graduated yet, I'll get to see you in person.
Yeah, I will be here for sure.
It's sort of a replacement for that one, Dana.
Sorry?
It's sort of a replacement for that talk.
Oh yeah, okay.
But we'll have you on campus next year. More questions? Perhaps one more? If not, thank you, Dana, for a great talk. We had close to 60 participants.
Yeah, it's fantastic.
Thank you all for joining us.
All right, Russ, best wishes. Everybody stay healthy. Get your shot.
Bye-bye.
Real soon. Hopefully, you youngins, hopefully you'll get it next month.
Yes.
Oh, I'm already all vaccinated. because I'm old and fat.
Thank you, Professor.